Hey guys, welcome back. I want to pick up where we left off, talking about the normal distribution, talking about how to work with a normal distribution, how do we get probabilities out of a normal distribution, talking about z-scores, which happen in the context of a normal distribution, and then trying to decide how common or uncommon is any observation inside of a normal distribution. So this is a helpful little image. Again, we have a generic variable x that we're assuming is distributed according to a normal distribution with some mean mu and some standard deviation sigma. These things are called parameters, right? This tilde is read as distributed as. Making this statement imposes this relationship, this bell curve relationship, on the different values of our variable x. And then we were talking about the fact that to get probabilities out of a normal distribution, it's different than for the binomial or the Poisson. For the binomial and the Poisson, that equation, that Poisson equation is the probability that our variable is equal to a particular value, right? This is the Poisson equation. And this is equal to the probability that our variable takes on a particular value of x exactly. For the normal, this probability for the normal distribution, this probability is actually 0, which is kind of weird. But if you think about this probability in a normal distribution being an area under a curve, you just think of finding, an infinitesimally small bucket or interval and looking inside of that interval, the area under this curve, and that is going to be 0 because we're dealing with a quantitative continuous variable. So the normal distribution, if we are imposing this assumption on the data, and it's an assumption, this is actually kind of a powerful statement because there is a lot that is known about the normal distribution. And that specifically is because we know how the mean and the standard deviation behave, and of course, the shape of this curve. So we know the mean goes right underneath that top point, which is also the median and the mode. And then we know this point probably right over here is -1 standard deviation. This point here is +1 standard deviation. Somewhere out here is -2 standard deviations. Out here is +2 standard deviations. And this is sometimes called the rule of thumb. Regarding probabilities. And it often says something like, I'm looking for the exact number, 68.26% of the data lies within 1 standard deviation of the mean. So if we assume that our data are normally distributed, we get to make this statement. 68.26% of the data lies within, that is ±1 standard deviation of the mean. So that means the probability of being in this interval is just over 68%. Okay. The other one that is quite common is that 95.44% of the data are within 2 standard deviations of the mean. And then if we extend this out further, -3 plus 3 99.07% of the data is within 3 standard deviations of the mean. Well, these are all rules of thumb. How did they compute these? Well, if you remember from your maybe calculus class, that an area under the curve is actually an integral, right? So if we compute the integral of this line between certain bounds, we're going to reproduce that probability. The other thing we get to do is we get to use the fact that the normal is perfectly symmetric. Skewness of a normal distribution is exactly 0. Normal is perfectly symmetric, which means if there's 68.26% from here to here, this means that in this area, there is 34.13% and 34.13% here. And that can sort of keep on going. We can divide these 95%, 0.44, into 2 halves and then figure out what this little bit is. And that is 13.59 and 13.59. It is not particularly important exactly what these numbers are. I do want you to see where they come from. So, from calculus, area under the curve is an integral. Now, before you guys start freaking out, we will not have to integrate in this class. And the normal distribution is quite difficult to integrate as is. But I would like to demonstrate that these are not just numbers out of thin air, that these numbers can be verified using any normal distribution. So the first thing to sort of think about is there is a special case normal distribution. Special case normal distribution. It is called the standard normal. And it has the mean of 0 and a standard deviation of 1. So any normal distribution that has mean 0 and a standard deviation of 1 is a standard normal distribution. And we actually have a special notation for it. The notation is Z. So if anywhere else you see the capital letter Z, most of the time the authors mean it is a normal distribution where the mean is 0 and a standard deviation is 1. So let's work with normal distribution. And what makes it important is just about, I'm not going to say all, but many of the probability tables out there that allow you to compute all of these probabilities, or not really compute, locate these probabilities, are made for the standard normal distribution. And then later in this lecture, you'll see why. But we can also just go ahead and work with a standard normal distribution. So for example, find the probability that our standard normal is between a -1 and a 0. So if I now start talking about a standard normal distribution. This point right here is my mean 0. This is -1 standard deviation. This is +1 standard deviation. This is -2 standard deviations. And this is +2 standard deviations. So the question I'm asking is, what is the probability that my standard normal variable is between -1 and 0? So mathematically speaking, right, I can integrate. And again, you will not be responsible for integrating, but the answer is -1 to 0 of the standard normal equation. Technically, it would be dz because it's with respect to the variable. So again, at the risk of being too precise, if I rewrite my standard normal equation, and this also gives me an opportunity to write out the equation of the normal. And why am I doing this? Because I don't want to portray this as anything magical, right? This blue line has an equation. It's an equation that makes this classic bell curve shape. So what we write is it's a function of our variable given our two parameters. Do you see how we read that? Similar to probability, this vertical line is read as given. All right, and here's the equation. Again, you're not responsible for memorizing this equation, but this is the equation of the normal curve, any normal curve. Alrighty. Kind of ugly, right? We have this 1 over sigma square root of 2 pi in here, e to the power of, and then there's complicated power. Can we track down where these parameters are? These parameters right here, right, are here, here, and here. So for the standard normal, the mean is 0 and the standard deviation is 1. So this curve becomes a little bit more manageable. All right, now I'm going to just put it right in here. And remember, my variable is z and not x. That's a technicality. And I'm going to write a little bit more neatly to make sure that this is all visible. There we go. So all I did was I flipped my x to a z because I am just following notation. I'm dealing with a standard normal. It's a z. So this variable right here is a z, which is nothing else than if I plug in 0 from u right there, and a 1 for this sigma right here. Just using the definition that the standard normal is just a regular old normal distribution, mean 0, standard deviation of 1. So if I just take this integral, right, from -1 to 0 of this expression, I will simply reproduce this number. So I uploaded a little document where I do this using Wolfram Alpha, and the answer is 0.34 1345. Okay, so these rules of thumb are out there for everyone to memorize, But how do they produce this number? Well, you simply integrate this curve from the one point to the other point, right? Because we want to find the area under the standard normal distribution between -1 and 0. And if we perform this calculation, we get the result we expect. There is also, in the document I posted, I do this using integration, and I also use a handy dandy online standard normal, just for any normal distribution calculator that allows you to perform this with point and click. You will fill out the mean and the standard deviation of your distribution. For the standard normal, it's 0 and 1, but you can apply it to any distribution. Not necessarily with a mean 0 or standard deviation of 1. And then you will go between -1 and 0, and you will find that number as well. But again, I want to show you how you would do this mathematically, right? This curve has an equation. This is the equation in general. This is the equation if we assume a mean 0 standard deviation of 1, which corresponds to the standard normal. We produce exactly the same result. And this works for any normal distribution, right? So you can, the same way, integrate this expression for any normal distribution with some mean and some standard deviation. If you don't want to integrate, no problem. There are calculators out there, including the one that I posted online, where you can pick whatever mean, whatever standard deviation, whether you're looking for between, below, above, things like that. So let's work a little bit with an example. So suppose that in the United States, the distribution of body mass index is normally distributed BMI, body mass index, by the way, I think this has units of kilograms per meter squared, is normally distributed. And probably more realistically, it is approximately normally distributed. But for this class, we will call it normally distributed. With mean 26.2 and a standard deviation of 4.4. Okay, so we can write BMI is distributed according to a normal 26.2, 4.4. And this is then the mean, and this is the standard deviation. I may have said this last time, but in some cases, people write the normal distribution in terms of the variance, which is sigma squared, and not the standard deviation. So you just have to be careful for that. In this class, I will always write it in terms of the mean and the standard deviation. So I can make a little graph here. Here is my BMI. This has units. Here is my normal curve, and I already told you this has a known equation. I will not rewrite it. Right in the middle here, that's not really middle. Right in the middle here, I have my mean mu. I know that is 26.2. Because that's what I'm assuming. And then, somewhere over here is -1 sigma +1 sigma. Okay, so we come to our next bit of new material, and these are called Z-scores. Z-scores. Z-scores are a tool to use inside of a normal distribution to find out where each observation lies in relation to the mean. It's a tool to use inside of a normal distribution to find out where each observation lies in relation to the mean. So the way to sort of visualize that is there's a scale, right? The BMI is one scale. We can simply reassign each one of our BMIs onto this Z-score scale, right? Every BMI will correspond to a Z-score, and every Z-score will correspond to a BMI. Here is the equation for the Z-score. This is going to be a Z-score of some observation It's a Z-score of some observation where our variable is some value, right? So little x is a value of our variable. In my example, this would be a particular BMI value, 20, 25, 35. What we do, we're going to subtract the mean, divide by the standard deviation. All right, so whatever the value, subtract the mean, divide by the standard deviation. So you will notice a few things. Positive Z-scores means you are above the mean, right? We're subtracting the mean, we're getting a positive number up here. Standard deviation is always positive. Negative Z-score below the mean. Well, naturally, what if you're at the mean? At the mean, Z-score equals 0. So right underneath here, I can put a 0. And then we have positive numbers on this side when BMI is above the mean. Negative numbers on this side when BMI is below the mean. Not that BMI is negative, but the Z-scores associated with these BMIs are going to be negative. The reason why we sometimes like to transform whatever it is we're measuring, could be BMI, could be blood pressure, could be concentration of some kind of protein in the blood, could be birth weight, could be air pressure, anything. The reason why we want to often transform from whatever it is we're measuring to a Z-score is because what we're measuring changes. The mean is different, the standard deviation is different, right? If I was measuring not BMI, if I was measuring blood pressure, this would be like in milligrams of mercury. So it would be something like 130 would be the mean, and I don't know, maybe 20 might be the standard deviation. But the Z-score doesn't change. Once you transform from whatever it is you're measuring to the Z-score, this Z-score always have a standard normal distribution. So let me repeat that. Regardless of what it is you're measuring up here on this axis, whatever your scale says, whatever your thermometer says, you can always apply this formula and get it to this Z-score scale. And on the Z-score scale, you are guaranteed to always have a standard normal distribution. So there's a mean of 0 and a standard deviation of 1. What that means is you can always tell how large is large and how small is small. You get a Z-score of 10, you know you are 10 standard deviations above your mean. You get a Z-score of 0.1, you know you are pretty much really close to your mean because you're only 0.1 standard deviations above your mean. With a BMI, well, I have to think, make an extra step, which is, well, what am I measuring? Is 10, how big is 10 on the scale of BMI? With a Z-score, those quantities are known. And I mentioned this before, just about all normal probability tables are written for this Z-score, for this Z standard normal distribution. So the probability tool that I have a link up for, the default that comes up is a normal distribution with mean 0, standard deviation of 1. So by default, you are working with a Z-score. You can change that. You can then change your mean to be 26.244. But by default, they're making you work with a standard normal distribution. So because we know what values of Z are sort of way in the tails of this distribution, we can always ask the question, how common or uncommon is my observation? So let's practice that. I'll write that down. Because the values of Z have a known distribution, regardless of X, whatever we measure. BMI, blood pressure, whatever. We can more easily evaluate Z for its magnitude. How large is large? How small is small? So let's practice this. For example, we can ask the question, how uncommon is a BMI of 24.5 inside of this distribution? How uncommon, how surprising is a BMI of 24.5 inside the USA distribution? So 24.5 is going to be clearly below my mean of 26.2. All right, so on my BMI scale, 24.5 might be right there. For me to consider how far away that is, I have to think about the standard deviation. That's, I don't know, about half a standard deviation away, right? But I can take this and then put it on this Z-score scale. Find the Z-score. Z of 24.5. Remember, we subtract the mean, divide by the standard deviation. Right, so we take 24.5, subtract the mean, divide by standard deviation. Subtract the mean was 26.2. Divide by the standard deviation is 4.4. So we get minus 0.386. As expected, our BMI was below the mean, so I have a negative Z-score here. And now, I'm still trying to answer my question of how uncommon or surprising is my BMI of 24.5 inside of this distribution. I can find the percentile. Right? Percentile is what proportion of the population is below that value. So when we're thinking about a test, you want to be in the 99th percentile because you want to be better than 99% of the class, right? You don't want to be in the 5th percentile because then you will only be better than 5% of the class. Hopefully no one's going to be in the 5th percentile. No, that'll be tough. Find the percentile. So we're looking for the probability that BMI is less than 24.5, or equivalently, probability that Z is below a negative 0.386. So let me take a look at these two statements. All that means is I want to find the area under the curve right here. This is my percentile. And that percentile is the same, right? The shape of the curve, that percentile is the same whether we're looking at the area below a BMI of 24.5 or the area below a Z of negative 0.386. These are going to be equivalent. So now, can use the probability table. Right, we've got to make sure if we're working with a Z-score, mean equals 0, standard deviation equals to 1. And then you're going to select below a negative 0.386. And that is equal to, well, what do you expect? We are less than half a standard deviation below the mean. So yes, we're below the mean, but we're not that uncommon. You remember that 68% of the data is within one standard deviation. About 34% of the data is, between the mean and one standard deviation below. We're somewhere in there. We're still towards the center of this distribution. What this number will tell us is it will give us a percentile. It will give us a probability of falling below this value. And that probability comes out to 0.3497. 0.3497, or 35th percentile. Not uncommon. Well within the interquartile range. Quick review, right? Interquartile range is the middle 50% of the data. And so it's between Q1 and Q3. Q1 is the 25th percentile. Q3 is the 75th percentile. What we got was smack dab in the middle, Q2 and the median, at about 35th percentile. We're well inside the middle 50% of the data. This is not an uncommon observation inside of that distribution. Plenty above it, plenty below. Now, you could, if you didn't want to use a probability table, you could integrate. You could punch into Wolfram alpha using my standard normal equation, the integration from negative infinity to negative 0.386, and you should get exactly that number, right? Because we're looking for all z below a negative 0.386, and technically this goes out to negative infinity. So you could still find this using integration. Or you can use the link I have up on our website, plug into our probability table, make sure it's set at mean zero standard deviation of 1, which makes the table use z-scores, standard normal distribution. You're going to select, you want to find out below, put in the z-score that you're dealing with, negative 0.386, and it will spit out the probability of falling below, which is, again, the percentile. Let's do one more. How uncommon is a BMI of 32? All right, let me redraw this a little bit. Oh, you know what? I'm just going to redraw. All right, here is my BMI scale. It's measured in units, kilograms per meter squared. Notice that z-score doesn't really have these units. The units of the z-score are standard deviations of our variable. We have a normal curve up here. That normal curve peaks. I'm terrible at drawing. The normal curve will peak. You know what? That's close enough. Here is my mu. There is my normal curve. I'm asking about a BMI of 32. BMI of 32 will, of course, happen above the mean, so it will be somewhere out here. 32. You could think on the BMI scale where you're saying, okay, I know the standard deviation is 4.4, and that's about one standard deviation plus some above my mean. So it's out there. It's out there. But the question is how uncommon? We want to come up with a number, right? So we want to say, find the percentile of BMI equal to 32. So two equivalent ways of doing it. This is the probability that BMI is below 32. And that's the same as probability that Z is below, okay? Find the Z-score. I know how to find the Z-score. It's a Z of 32. I'm going to take 32, subtract the mean, and divide by the standard deviation. And this computes out to 5.8 over 4.4. Which is 1.318. So 32 is 1.318 standard deviations above the mean. I'm trying to find the percentile associated with a BMI of 32 because I'm trying to quantify how uncommon a BMI of 32 is inside of that distribution. So I can find the probability of falling below on this scale, but this is the same as working with the Z-scale. And why below? Because I'm using the definition of where a percentile is. At this point, I can either integrate, take my normal curve, plug in from negative infinity to 32 of my normal distribution. I can integrate the standard normal curve from negative infinity to 1.318 of the standard curve and find this probability, or I can use my probability app. Okay, if you're using the Z-score, ensure that the mean equals 0 and the standard deviation equals to 1. And then you're going to select below 1.318, and it will spit out a probability. And if you're following along, in a normal distribution, the mean is also the median, right? And we know from one of the earlier classes that the median splits the data into exactly 2 halves. So below the median, also the mean of the normal is 50%. We want to know below some number that is above the mean. So we're expecting a number that is going to be greater than 50%. And that number is 0.906. 0.906. So about 90th percentile. Uncommon. Right? We are now way outside of the interquartile range. The interquartile range, of course, goes from the 25th to the 75th percentile. Now I hear the question, how do you decide how far out is uncommon? Well, we're gonna cover that in the next couple of lectures. But for now, I want you to get used to quantifying how surprising or uncommon something is inside of a distribution. We computed a BMI of 24.5, and that was just below the mean. Oh, I don't know, 0.3 standard deviations below the mean. This one is about 1.3 standard deviations above the mean. The first one was well within the interquartile range, and I'm saying the interquartile range because it's a convenient way to say middle 50%. Quite typical value inside the interquartile range. This probability came out to 0.906. It's the 90th percentile. Well, we have an idea of percentiles. A lot of standardized tests use percentiles. A lot of clinical metrics use percentiles. We know something in the 90th percentile is quite uncommon. Only 10% of the population 10% is above. How do I know that? Well, because this BMI of 32, equivalent to a Z-score of 1.318, is the 90th percentile. 90% below, 10% above, right? So the other way of looking at it, this is the top 10% of the data. And in this case, maybe not the greatest top 10% to be at, because this is the BMI, and we know BMI has health-related correlates. BMI is not the be-all, end-all, but it can often be a convenient metric of general health with some very well-known caveats, for example, athletes being one. All right. So at this point, we have talked about Z-scores. We have talked about how telling an example of a common observation and an uncommon observation. There's only one thing left to do for this lecture. I'm going to just redraw again. So thus far, we have started with an observation and asked the question, well, how common is that observation? So we want observation to probability thus far. What if you go the other way? You go probability to observation. Okay, here is my BMI scale. I know inside of a normal distribution, there's always a scale of Z-scores that I can work with. And I know that I can always take a BMI and transform it to a Z-score by subtracting the mean and dividing by the standard deviation. And I know that my Z-score, by the way, I like to think of a Z-score as like a one-dimensional GPS, because it always lets me know how far away I am from the mean, right? The one-dimensional GPS. At the mean, it's 0. I know below the mean, we get negative numbers. Above the mean, we get positive numbers. How we learn something, we repeat sometimes. So I'm sorry that I'm repeating myself, but I'm trying to sort of get this picture sort of ingrained in your guys' brains. Thus far, we're giving ourselves an observation. We're asking a percentile or a probability. Let's work backwards. Suppose that individuals in the top 10% are eligible to be enrolled in a new NIH obesity study. Suppose that individuals in the top 10% of our BMI distribution are eligible to be enrolled in a new NIH obesity study. What is the smallest BMI eligible? So kind of weird wording. Why did I say the smallest BMI? Well, we're looking for the top 10%, right? So these are small BMI values. These are large BMI values based on how a number line works. Here is the mean, right? 50% below, 50% above. We know I'm looking for the top 10%. Top 10% are going to be, or is it 10, or did I ask for less? I asked for less than 10% because we had 10% on our previous example. So let's do top 5%. We only have so much funding. Top 5% of the individuals. Top 5% are going to be right out here. So we're looking for this threshold here. You can see that, you know, a crazy BMI of like 55 is in the top 5%. We know a crazy BMI of 65 is in the top 5%. But we're trying to find this threshold or the smallest BMI that is still eligible. So this is equivalent to asking ourselves, well, what is a Z-score? Right? This is equivalent to asking what Z-score leaves 5% of the data above itself. So, to recap, we're not interested in a Z-score, right? When we're enrolling patients, we're interested in their BMI. We're going to compute their height, we're going to compute their weight, and we're going to compute their BMI. But, you know, it's very often easier to work on the Z-score scale. And asking what is a BMI that leaves 5% above itself is the same as asking what is the Z-score that leaves 5% above itself. So at this point, if you were working with a printed table, you would look in the middle of that table and you would try to figure out what is a Z-score that leaves 5% above itself, 95% below, right? So another way of thinking about it is what is the Z-score that is in the 95th percentile of this distribution, equivalent to what is the BMI in the 95th percentile of the distribution. So now we can use our little app, probability app. And you guys are going to get a chance, either, you know, play around with it before the activity, or we'll play around during the activity with the probability app. Going to select values from an area. That's not the default. We're going to select area equals 0.05, and we're going to make sure that we have above selected. So the picture in the app needs to match the picture in our brains, right? Or as we're trying to figure this out, you draw this picture. Because if you don't select above, or if you have below selected, it will be on this side of the distribution. It will select the bottom 5%. That's not what we need. This question is asking about the top 5%. So you're going to click values from an area, set that area to 5%, 0.05, click above. The handy dandy app will produce a Z-score of 1.645. And again, if you're working with a Z, make sure the mean is 0, standard deviation is 1. That makes a Z-score. If you're not working with a Z-score, if you're working with the BMIs, you have to match up the mean and the standard deviation. But by default, this probability app, by default, mean 0, standard deviation of 1. All right, so that number, 1.645. Cool. Are we done yet? We're not. We're not done. Because we have a number on the Z-score scale. We now need to transform this back from the Z-score scale to the BMI scale. So I have 1.645 is equal to, all right, now we have to think back to the formula of the Z-score. Remember, it's X minus the mean divided by the standard deviation. So I'm looking for X, right? But I have the mean. I know what the mean is, 26.2. I know what the standard deviation is. It is 4.4. At this point, algebra. All right, multiply both sides by 4.4. Okay, add 26.2 to both sides. And now we have solved for our BMI. So we're looking for something that is 4.4, 1.645 standard deviations above our mean. That number is 33.43. That is the smallest BMI that will be eligible to be enrolled. That is the BMI such that 5% of the data are above, 95% of the data is below. And that is equivalent to asking, well, what is a Z-score that leaves 5% above, 95% below? And that number is 1.645. How do we know that it's 1.645? We used the handy dandy probability app. We picked values from an area. We made sure that we're working with a Z-score, right? Z-score means we're using the standard normal distribution. Remember, Z-scores always have a standard normal distribution. Standard normal distribution means mean equals 0, standard deviation of 1. So we have value from an area. We select area of 0.05. Why 0.05? We're looking for the top 5%. Top 5% means we also have to select above. If we wanted the bottom 5%, we would select below here. That's not what we need. We need above. We make these selections, out comes a Z of 1.645. All right, so that means I have a number on the Z-score scale. I now just need to get it onto the BMI scale. How do I do that? I apply the formula. I know this is the formula where I have Z of some observation is X minus mu over sigma. I have the Z-score, I have the mean, I have the standard deviation. I apply algebra to solve. Okay, I know that was quite a bit of repetition, but that was planned repetition. The key is to set up the picture. Don't be afraid to draw the picture when you're trying to find the probability necessary. Overall, we now have begun working with a normal distribution. We now know what a Z-score is, and we can figure out how common or uncommon a Z-score is going to be. So that sets us up for a very important topic that is going to happen the next bit of new material, just hypothesis testing. This entire bit is leading us to hypothesis testing. So we're going to pause it here. I will see you guys in person in a couple of days. Thank you guys for your attention. And be well. Take care.